Welcome back to Module 2, Part 2 of the International A-Level Physics Getting Ready to Teach. I'm assuming most people were here for yesterday's session. I'm recognising most of the names on the list there. So although I will recap over one or two things from yesterday, I won't spend a lot of time going over things from yesterday, but move on to today's material. My name's Keith Penn. I've been a teacher of physics and electronics to A-level for 33 years and now work as a lead trainer for sciences for Pearson Edexcel. And I'm coming to you today from a lovely warm autumnal day and quite sunny day in just outside Cambridge in the UK, where it's just 9 o'clock in the morning. Okay, in this training, we'll be looking at understanding the assessment objectives and the question types, the mark schemes for those questions, and we'll practice using the mark schemes using exemplar student work just a little bit, and hopefully learn a little bit about the support provided by Pearson around assessment and exemplars. Yesterday we looked at introducing the content of the specification and preparing to teach it. We're focusing on the assessment and examination of this specification today. So let's begin. Okay, as mentioned yesterday, Pearson is the world's leading learning company and as the UK's largest awarding organisation, best placed to provide qualifications aligned to the British educational system. We're a trusted partner to 6,500 schools and employers globally, marking over 10 million exam scripts and operating in 70 countries worldwide. Assessment review. Yesterday we had an overview of the content of the topic. We'll just have a brief review of the way in which it's assessed. So I mentioned this yesterday, just going over because this is what we're focusing on today. Unit 1 and Unit 2 and 3, you'll remember, are the assessments for the first half of the full A level or the International Advanced Subsidiary, the IAS. And so Units 1 and 2 are content modules for that part. Both have 1 hour 30-minute exams, and they include all the types of questions listed at the bottom there. Unit 3, on the other hand, is slightly different in that it's assessing the experimental procedures, knowledge and understanding of experimental procedures covered in Units 1 and 2. And that's a slightly shorter exam, 1 hour 20 minutes. And that includes all the same types of questions except for multiple choice. No multiple choice questions in the Unit 3. And reflecting that same pattern, the 3 further modules, the units which add up to the full advanced level, Units 4 and 5 are the content modules and Unit 6 the practical skills module. So Unit 4 and 5 both have slightly longer exams, 1 hour 45 minutes each, and they too include the same types of questions that we've just seen in Units 1 and 2. And then Unit 6 assesses the practical skills, the experimental procedures developed during Units 4 and 5, and that too is a slightly shorter written exam, 1 hour 20 minutes, and it includes all the same types of questions except for multiple choice. So no multiple choice questions in Units 3 and 6, but multiple choice and all the other ones in Units 1, 2, 4 and 5. The assessment objectives underpin the construction of the paper. So the number of marks that are allocated, for example, to assessment objective 1 will determine the number of questions that can be asked in a particular style. So you can see assessment objective 1, demonstrate knowledge and understanding of science, effectively recall element of the learning, and amounts to about 35% in the IAS and about 30% in the IA2. So a total over the whole A level of about 33%, with a very small tolerance on either side of that. So the examiners have quite rigid guidelines within which they can ask questions testing recall of the content. Over recent years, assessment objective 2 has been split into 2. So there's part A, application of knowledge and understanding of science in familiar and unfamiliar contexts, which is what it used to say, and B, analysis and evaluation of scientific information to make judgments and to reach conclusions. And you can see also the percentages there that those questions amount to in the AS and the full advanced level. And then assessment objective 3, experimental skills in science, including analysis and evaluation of data and methods, is 20% of the total. So it's worth saying AO2B is relatively new. It's new to the grid in this specification. And it's also worth indicating that AO3, the experimental skills one, is only tested in units 3 and 6. There are no assessment objective 3 questions in papers 1 and 2 and 4 and 5. If we break that down still further, you can see here shows the weighting of the assessment objectives in the IAS and the full assessment IAL qualifications. Not going into great detail of the tables, these tables are within the specification, but it is just worth mentioning that there's slightly more emphasis on application and correspondingly less on recall in the full A level. So if you look at the A level modules 4, 5 and 6, the percentages for assessment objective 1, the recall one, are slightly lower, and the corresponding percentages for, especially for AO2, are a little bit higher. So as you'd expect, the second part of the advanced level is slightly more demanding on students' understanding and application than the AAS, the early modules. And that's kind of reflecting the fact that students are developing those skills. Hopefully, that's the intention as they go through the specification, as they go through the course. So let's have a look at examples of those question types. We mentioned those different types of questions. We'll just look at 1 or 2 examples of each one. So the next 5 slides show examples of these 5 categories of questions: multiple choice, short open, calculations, open response, and extended writing questions. Remember, papers on the practical skills units 3 and 6 have all of these 5 question styles except multiple choice. So just the last 4. So multiple choice questions. Okay, as is standard, they have a fairly straightforward question, and 1 of the 4 answers is correct. So students simply have to indicate with a cross in the box. You can see on your screen perhaps that there's a very faint white cross on a sort of grey background. So students put a clear cross with black pencil or black ink in that box alongside the one that they think. So car is travelling at a velocity v. The driver applies the brakes and the car decelerates until it comes to rest. The work done by the brakes on the car is W. Which of the following expressions linking W and V is correct? W proportional to V. Option B is W proportional to V squared. Option C, W proportional to 1 over V. Or D, W proportional to 1 over V squared. It's worth students being aware that there's no penalty for a wrong answer. There's no advantage in leaving the answer blank. It's heartbreaking to see students' papers where they've left several questions blank perhaps because they didn't know the answer. Even if they're not absolutely sure, of course, a complete guess will give you a 25% chance of getting a correct answer, and they can improve their odds of getting a correct answer by eliminating those answers that they know to be incorrect. So if, for example, they know it's going to be either A or B, not possibly C and D, they could already reduce their odds of getting the right guess to 50%. So they can improve. There's no point in leaving it blank. Sometimes I think students think they start with a pile of marks, and when they get a wrong answer, a mark is knocked off. That's not how it works. So there's no disadvantage to students in putting an answer in there. There's no advantage to leaving it blank. Here's an example of part of a short open question. The full question has several parts like this, including calculations. You can see that the marks that are available are indicated. All of the multiple choice questions have 1 mark each, but the other questions, which have different weighting, it indicates in the number in brackets how many marks are available. And it gives an indication of how many points, how many points within the answer students need to be aiming at. So a 2-mark answer, a question which is worth 2 marks, they're not going to get full marks by a 1-word answer. They need to put 2 points in there. So in this case, it says a light-dependent resistor, LDR, has a resistance of 6,100 ohms when illuminated with indoor lighting. Explain how the resistance of an LDR changes with illumination. Your answer should include reference to conduction electrons. When there's a statement like that in a question, what it should include, it's not just a hint that that might be a good idea. It's the students need to take that as an instruction. An answer which doesn't include reference to conduction electrons is never going to gain both marks. So an indication in a question about what they ought to include, they must take as an instruction. Their answer must include that, or they're not going to get both marks. As we mentioned before, this is the command word here is explain, so their answer is going to have because, or a word that means because in there. They're going to need to say what happens, and this is because, and that's where their reference to conduction electrons is going to come in. Here's an example of a calculation part question. As before, the full question has several parts. And again, the number of marks that are available for the question are indicated. You can see here there's a 3 in brackets. So there are 3 marks available for a correct calculation here. It will be essential for students to show their working out. Sadly, a fully correct answer with units will gain the full 3 marks, even if they've shown absolutely no marking. So if all they write is the correct answer on the bottom line with the units, they will get full marks. But if they've made any error whatsoever in one of the preceding steps, obviously if all they've written is the answer, if that's wrong, they can't get anything but 0. But if they've shown their working, if they've made a simple error, and it's really easy to do so, even for a good conscientious student in the stress of an exam situation, if they made a simple error, if they've shown their working, it will still be possible to gain perhaps 2 of the 3 marks, in this case by use of the 2 key equations, phi equals AF and C equals F lambda. So if they've tried to use those 2 equations, even if they've messed up the calculation, they can still get 2 of the 3 marks available. So please, please, please encourage your students to always show their working out. I have to confess, I did mention I've been teaching for 33 years. I'm one of those old-fashioned teachers. I won't mark a student's working class unless they've actually shown their working out. If all they've put is a number, it goes back unmarked. But the examiners are gentler than I am. They will mark a question. And if, as I say, if it's got the right answer, it will get full marks. But please, please encourage them every time to show their working, because it will allow them most of the marks, even if they've made a simple error or pressed the wrong button on the calculator. They can still get credit for what they've done correctly. Open response questions. This is an example of an open response part of a question. You can see it's worthy of 4 marks. The full question has several parts, and there are quite a lot more lines in the actual paper than are shown here for the response. So you can see it says the diagram shows the path of a beam of light traveling from a light source in air through a 45-degree glass prism. The path taken by the beam of light is shaded. The critical angle for glass is 41 degrees. Explain the path of the beam of light. Okay, 4 marks available for that. So it's going to need some detail and some linking between the various comments and facts that they put in their answer. And we'll look at mark schemes for these in a little while. And here's an example of an extended writing part of a question. As I think I mentioned yesterday, physics students, even the most able physics students, tend to be better at doing calculation questions, even extended calculations, than they are in questions which require some extended writing. Maybe their language skills, it may be that students have chosen physics rather than literacy-based courses, languages, English, history, and so on, because of their lack of love for writing essays and so on. But whatever the reasons, students of physics tend to do better in calculation questions than they do in extended writing ones. So it behoves us to give them some significant practice in doing this, because this is an area that again and again examiners suggest that students do less well. As you can see in the full page smaller image, a significant space is provided for the candidate to answer. Students should be encouraged to attempt these and the open response questions shown on the previous slide, even if they're not confident of getting full marks. It's actually very uncommon for students to achieve 0 marks. this question is worth 6 marks. And the first 2 marks are available for fairly simple information. So even a student who isn't confident of getting to the end of the question, please encourage them to make an attempt. As I say, it's very rare for a student who makes any attempt to actually achieve 0 marks. So it's well worth having a swing at it, even if they're not confident of getting to the end. The mark scheme for this question starts with this phrase. This question assesses a student's ability to show a coherent and logically structured answer with linkages and fully sustained reasoning. Marks are awarded for indicative content and for how the answer is structured and shows lines of reasoning. So I really need to emphasize that just recall of indicative content alone does not score full marks. They can answer with bullet points, but if they're just disconnected bullet points, that's not going to get the full 6 marks. In order to score full marks, there need to be some linkages. They need to say how their various statements link to each other. This happens and this happens, and because of that, this happens. So making links between the statements. And that's the bit that candidates find hard. In most cases, the maximum out of the 6 that can be scored for content alone is 4 marks. So getting those 5th and 6th marks is going to require students to provide a sort of logical sequence, so explaining how their statements link to one another. That's going to need practice. Let's have a look at the mark schemes for this spec. Here are screenshots just to the front page of a number of mark schemes from last year. What are the mark schemes and the examiner reports? Well, the mark schemes, obviously, I guess, are the answers to the questions, but they often give a number of alternative answers that students might give. They can show indicative content to guide the markers, and they also advise a marker of common errors and what you can credit and not credit. So which errors can be given some marks and which ones really can't be credited. So it's the go-to place for how many marks you can award for each type of answer. Examiners are encouraged to use the mark scheme positively and to look to reward marks for what is there rather than penalise students for what isn't. So here's an example. It's a screenshot from a section of the mark scheme to paper 2. Not really to read through in detail, there's too much information on there, it's just really to illustrate the type of information that's contained within the mark scheme. Under answer, the second column in, the type of answer that's required, as well as acceptable alternatives are shown, and further clarification where needed. The total marks that are available are shown on the right-hand side. So for example, at the bottom row here, 13BII, you can see that down the right-hand side, it lists 6 possible places where marks can be gained, but the total possible mark for that section is 3 marks. So that even if they vote both alternatives, the maximum they can score on that part is 3 marks. So the maximum marks for the whole question 13, written down at the right at the bottom, is 7 marks. Notice that there are no marks in this occasion for quoting the formula, but for using it. So in the example 13A at the top, it's the rearranged formula that gets a mark, and the evaluation, W equals 7.92 times 10 to the 5, that gets the second mark. So it's very clear in the mark schemes what can be awarded and what can't. That's the intention. Here's a screenshot of the top and the bottom half. I've split it this way just to fit it all on one screen. The full mark scheme for an extended writing question. As before, I'm not planning really to go through this in detail. It's to give you an indication of the way in which the mark scheme is laid out. But it is worth pointing out that this type of mark scheme awards marks for a number of indicative marking points. That's the table at the top of the page, so over on the left here, how many marks you get for a number of indicative marking points. So if you look at that table, if they got 6 indicative marking points, they can get 4 marks, and so on down the table, down to 0 at the bottom. There are also marks awarded, and you can see that in the second table over on the right-hand side of the page here, Marks awarded for structure and lines of reasoning. Examples of suitable indicative content then are shown at the bottom of the page. So you can see those bullet points down at the bottom are examples of indicative content that can score towards the content part of their answer. Links to resources used. These are from the mark schemes themselves. I will be showing you later where the website is, but on the website, all of these mark schemes come under the examination materials. You remember we looked yesterday and it said there was something like 234 past papers with mark schemes and examiner reports, and they're all within there. If they have written formula given in the data book, but the evaluation is wrong, is the mark awarded? In this specific case, the example we just looked at, the answer is no. There will be some questions where the mark scheme says quoting the correct formula will be awarded a mark, but it's almost certain that if that formula is in the data book at the back of the exam paper, they won't get a mark simply for quoting something that's written there. If they have to recall a equation and that's part of the mark scheme for that question, then they could get a mark for that. But in this particular question that we just looked at, where are we? This one here, no, the formula was quoted, was given, so they only get a mark for using it correctly. So if they've used the formula correctly, but the evaluation is wrong, you know, if they've tried to use it, substituted some numbers and then messed up their calculation, they can get 1 mark for that. But if all they've done is written the equation and not tried to put figures into it, they can't get a mark. It's worth us spending just a little time looking at the general marking guidance. This appears at the start of each mark scheme, this or something like it, and it addresses some common misconceptions which can arise when teachers have not themselves been exam markers. I particularly want to draw attention to phrases which emphasise that wherever possible, the aim is to credit good work rather than to punish errors. It's worth saying that when teachers engage in marking or moderation exercises, marking blind student attempts at exam questions, and then perhaps comparing their marks with those awarded by the real examiner, then teachers almost invariably mark more harshly than examiners do. That tends to be because we tend to penalise errors, and that's not what the examiners are doing. They're trying to credit correct work and kind of ignoring errors unless they actively contradict what they're trying to say. You know, so we tend to be slightly harsher markers, and that's why it's worth looking at these mark schemes and exemplars to get in line with what it is that the actual exam markers are doing. Mark schemes should be applied positively. Candidates must be rewarded for what they have shown they can do rather than penalised for omissions. There's no ceiling on achievement. All marks on the mark scheme should be used appropriately. Question, what about not writing the unit with the numerical answer? In most cases, that would not give them the full marks, but it will specify in the mark scheme whether or not the correct answer needs the units. Normally it would, but in some questions, as you'll see, the units are already on the bottom line there, so they just have to put the value in. So sometimes the unit is a marking point, sometimes it isn't. It's always, of course, good practice in physics. You know, a number without a unit, unless it's something like a ratio, a number without a unit is not a full answer. But yeah, it depends on what the mark scheme says. As I mentioned much earlier on, there's a very tight percentage of questions which can be based on recall, and another tight percentage which questions can be based on understanding and application. And if they make the units a marking point for every single question, the recall would exceed the number that they're entitled to do. So it won't be a marking point in every single answer, but it's always good practice to put that. Yeah, it will usually make it clear that they need to put an answer with units. Always good practice. Ditto significant figures. Again, sometimes it'll be a marking point, sometimes it won't. At GCSE, you know, the lower level, unless the question states the significant figures are required as part of the answer, then that will not be a marking point. At A level, it tends to be a little bit more demanding than that, and normally students will be expected to write to the correct number of significant figures, but the mark scheme may allow some leeway in that. Obviously, the normal practice would be for the answer to be quoted to the same number of significant figures as the least precise value that goes into the question. But I think there's usually a little bit of leeway on that within the mark scheme, unless it specifically says write your answer to the appropriate number of significant figures. But you can guarantee that if a student writes down every number that's on the calculator and puts 15 or so significant figures, that will not gain the marks. So the general answer is yes, the significant figures will be included within a correct answer. Okay. Where did I get to? What if the answer is not exact as per milliseconds? Is that what you mean, MS? As per manuscript, perhaps, but as per mark scheme, sorry, I wondered what the MS, thank you. What if the answer is not exact as per mark scheme or close to it? The mark scheme will say what tolerance is allowed. So if there's a calculation, it will often say credit any answer that is between and then give the tolerance that are acceptable answers. That's particularly true if, for example, students are taking readings off a graph where there is a little bit element of judgment. It will say accept answers between this and that. Yeah. And so, yeah. What if the student's answer includes all points in the mark scheme, but there are still some wrong ideas? Will he or she get full marks? And the answer is yes. If all the points in the mark scheme are met, then they will get full marks, even if there are errors in there or wrong ideas. And that's where I kind of say it's different often from how we as teachers sometimes mark. Obviously, as a teacher, you'd want to point out to the student that there's an error here. But in an exam situation, the marker's not in a position to have a dialogue with the student. And the straightforward rule is if they've met the criteria for all the marks on the mark scheme, they will get full marks, even if there are errors within there. So third point down here, all the marks on the mark scheme are designed to be awarded. Examiners should always award full marks if deserved, i.e. if the answer matches the mark scheme. When examiners are in doubt regarding the application of mark scheme to a candidate's response, the team leader must be consulted. And crossed out work should be marked unless the candidate has replaced it with an alternative response. It's well worth students being aware of that. If they scribble it out so it can't be read, if they think they made a wrong answer, then clearly that can't be marked. But if they put a line through it, so it's still visible, if the correct answer is in there, they can still get marks for that. So do encourage students simply to put a line through an answer if they think they got it wrong, rather than to scribble it out completely, because they can still be awarded marks if they actually had got something right in there. Where had we got to with the questions? What if the answers include wrong physics or contradiction in the answer between the correct answer and the wrong answer? If part of their answer contradicts the other part, that will cause them to lose marks, because obviously otherwise students could hedge their bets. You know, if, for example, a question is a straightforward yes, no, and they said sometimes yes, sometimes no, they're hedging their bets. They couldn't possibly lose out on that. So no, if they've covered all the bases with the possible answers, they won't get full marks for that. But if they've included some wrong physics, but it doesn't actually contradict the right parts of the answer, they can still get the full marks within the answer. They are always looking to credit correct parts of the answer rather than to penalise incorrect parts. Can a learner get full marks for calculation with an errors carried forward? Not for the full question, because the point at which they made the error, they will lose mark. But the principle of errors carried forward is that you only lose the mark on the first time you make that error. If you, for example, put in an incorrect piece of data in the first step of a question, and then correctly use the answer to that, which of course is an incorrect answer, but if you correctly use that in the rest of the calculation, all of the other points are available. So you'd lose the mark at the step where the error had been made, but can still be awarded all the subsequent marks for the other parts of the question. That's basically what errors carried forward means. It means you're only penalised once for one error. Otherwise, you'd be being penalised more for errors that you made early in the question than you were for errors that were later in the question. Okay, so that would yeah, that's the principle of errors carried forward. It means that the marker the examiner will use a calculator themselves to work through the calculation using the incorrect data that the students use. And if they've correctly done the rest of the calculation with the incorrect data, they can still get the rest of the marks. If question has values in 2 significant figures and students given 3 significant figures, usually, I mean, the mark scheme will be specific on that, but the usual case will be that will be accepted. As I say, if they've given it to 15 significant figures, it will be laughed at and wiped out. But if they've written it that close, unless the question specifies that the exact number of significant figures will be an important part of the answer, then that it would normally allow that amount of leeway. But the mark scheme will be the thing to refer to each time about that. What if candidate shows 2 workings or 2 answers on the answer line? 2 sets of workings would usually be okay. They'd be credited with, you know, the correct one, if you see what I mean. Or it might be 2 alternative ways of working it out. 2 answers on the answer line, a bit more difficult. That's almost certainly going to be marked wrong. If they put 2 possible answers on the answer line, no, they have to make a decision on that, because what's on the answer line, the marker is going to take as the answer. But as I say, if they've tried 2 alternative workings and then made a selection on what they put in the answer line, if that's correct, they could still get full marks on that. Okay, thank you. Where were we? Here we go. So consider for a moment which assessment objective or objectives are being assessed in this part of an exam question. Here's the exam question on the right-hand side of the screen. A student carried out an experiment to determine the resistivity of a metal in the form of a wire. She made the following measurements: length of wire 0.2 meters, resistance of wire 50 milliohms, diameter of wire 0.36 millimeters. Determine the metal of the wire using information from the table below, and then it gives the resistivity per ohm meter, sorry, the resistivity in ohm meters for aluminium, tungsten and iron. I'm not asking you to answer the question, but to say which assessment objective or objectives are being assessed in this part of the exam question. If you're putting AO2, by the way, you're doing what I've just accused students sometimes of doing, which is hedging your bets, because remember, AO2 is split into 2 parts. So are you saying AO2A and B, or AO2A or AO2B? Be specific. I'll just try and pick up the question from Karja before that disappears up the screen. If different mark scheme has different bullet point for same type of question, can he get a mark if that bullet point is not from that paper's mark scheme? In most cases, if the mark schemes will give the most likely indicative content, but if the student has put another piece of indicative content which is correct but doesn't happen to be in the list on the mark scheme, that will be allowed. That will be get marks. If it's relevant and a correct answer to the question, then there's leeway for the marker to give that. And sometimes it will say in the mark scheme things like, or other correct alternatives, or words to that effect, and so on. So yes, if the physics are correct and it's relevant to the question that's been asked, rather than just something else that they know about that topic, if it's relevant to the question that's been asked and correct, they will get a mark for it. Going back to our question on the screen, the answer is AO2B. Okay, AO2B. The examiner report that went with this question suggested that this was the first question that had been asked in the new specification which targets this new assessment objective, which is why I picked it as an example here. Remember, assessment objective 2 has been split in parts A and B, where A is the application of knowledge and understanding of science. B is analysis and evaluation of scientific information to make judgments and reach conclusions. And that's what students are being asked to do in this question. They're being asked to analyse the scientific information in the information at the top and the table underneath to make a judgment and to reach a conclusion. They're being asked to determine the metal of the wire. So their answer would need to show some working of how they've but then determine, they would need to state which wire they think it is. These open-ended questions require a justification. Simply stating that the answer is a number would not score the marks. Excuse me. Many candidates who scored nothing in this question gave an answer without any justification or, or conclusion, and so didn't score. So in many cases, it's the command word, it's the command word that gives away the assessment objective that it draws upon. So the command word here is determine, and that's very specific. They're being asked to make a decision, so the answer would need to include what that decision is. I'm going to look at this question on the right here. The photograph shows a machine used for surveying the seabed. A communications cable connects the machine to a ship on the surface. You can see the communication cable labeled on the photograph and then the internet source of the photograph. The material used in the outer casing of the communications cable must withstand the large pressures at the seabed, yet be light enough to lift out of the water. And then it gives the density of Kevlar and the density of steel. Deduce whether steel or Kevlar is more suitable to use in the outer casing of a communications cable at the seabed. And you can see this is a 4-point question. How can we encourage students to develop confidence in tackling questions such as this one? They will have been taught about densities and other properties of materials. You know, it comes within the specification. If they've covered the specification, they'll be taught those things, but very unlikely to have taught it in the context of this, a cable being used to attach a ship to the machine down at the bottom on the seabed. So it's a different context application to the one in which they were likely to have learned about densities and other properties of cables and other things. How can we encourage students to develop confidence in tackling questions where the context is different from that in which the concept was initially learned? It's a regular problem, and examiners in their reports say again and again that these types of questions students really struggle with. They've learned the physics. If they were asked the physics as it appeared in their textbook or in the lecture where they initially learned that, they would almost certainly be able to answer it. But when it's asked or posed in a different context, you know, where the problem is set in a different context to that in which they learned it, students often will think, whether they say it out loud or not, they'll think, I haven't learned this. I haven't been taught about machines on the seabed and communications cables. They find it hard to apply their learning to a different context. How can we as teachers encourage them to develop confidence in this? Because there's absolutely no question we need to do that. The examiners won't just by accident set questions in a different context. They are required to do so. You know that every single physics paper for A level, advanced level, is going to include questions where the question is set in a different context from that in which it's normally been presented during the teaching. So how can we develop their confidence in doing that? I'll just give a moment or two for anybody to put comments in the chat box, and then I'll go on to discuss it. Giving them problems of this nature during their course and discussing them, absolutely. The more examples we can give of different context questions, when we've learned some new physics, look at other questions that use either past paper questions or questions from elsewhere that use other contexts to tackle that, that's going to give confidence that that's the sort of question they're going to get asked in the future. Use case studies during teaching, yes, and particularly real world ones, bringing in ideas from news reports, internet articles, things from like New Scientist, Scientific American, scientific magazines, where students are being asked to apply their learning to a new problem, always good. By using questions such as this one for discussion in class, I can't thank you enough for that answer. I think class discussion on these things is infinitely more useful than simply setting written questions on them, because that's where the rough ideas, the rough edges of people's ideas and misconceptions are knocked off. You can get through a lot of discussion of what works and what doesn't, and how you can apply our learning to different contexts in a class discussion where it would take several sheets of questions to get to the same point. So really, really good point. Encourage them to read, underline and circle the question asked, and then think which chapter this question is related to, and think of the formula and principle, and then try to attempt them. That's right, they need to refer back to where did I learn the physics? Which physics did I learn that's applicable to this situation? Use as many examples that you can from past papers and allow them to mark these answers. Absolutely right. If you're in on the GCSE session, you'll remember the thing called access to scripts, thank you, where you can download students' answers, where you can download your own students' marked scripts immediately after, and they can be really valuable learning resources for future cohorts of students. You can look at examples of how students in your own school answered these questions in the past and get current students to mark those answers or to discuss and say, why is this a good answer? Why is this one not so good? You make them anonymous, of course. You're not trying to ridicule or humiliate or embarrass the students who've done their exam, but you can use those examples. You're absolutely right, Jane, and I understand that's a limitation, but if it's online learning, does it still allow, as we're having here, the opportunity for some type of discussion? Is there two-way communication? Can the students communicate with the teacher as well as the teacher with the students? Because if that's the case, it's still possible to have that sort of input. Oh dear, that's unfortunate. Yeah, I don't know whether it's possible to ask whether that's a thing that can be built in, whether by email or chat room or whatever. But I think not having discussion does restrict students' learning, particularly at advanced level, I think. Also ask them to find examples which work on the principle we're studying. Absolutely, yes, yes. More general question there, Carter, and I'm going to have to think about that one. Do the student need to get the overall 240 marks from 6 units of physics to be eligible for cash-in? Are they eligible even if they are unqualified in any unit, or do they need to qualify? No, I think it's the overall mark that allows them to cash in for the grade. So there isn't a pass mark per unit, it's the pass mark overall, which are joined together, as it were, so they don't have to achieve an individual pass mark to each unit. That's my understanding. Students are all in different places in their course as well. Okay, you have got some serious difficulties there in terms of some of the strategies I'm suggesting. Yeah, I do accept that. Okay, just going through notes I've made on this before as well. Thank you very much. They're really helpful contributions. Uh, The principle embedded in AO2A is application of knowledge and understanding of science in familiar and unfamiliar contexts. It will be impossible to second guess and teach in advance every possible different context which examiners might come up with. The key to what we're talking about is in developing confidence, as it was worded in the question on screen, developing confidence in students that they've learned the scientific knowledge and understanding and have the ability to apply it to understanding other similar situations where the same scientific ideas and principles apply. And we develop this confidence by regularly asking and discussing such other context questions, as several delegates have suggested here. By regularly asking and discussing these questions, and also perhaps by reading and discussing science-related items from the news and other resources where we can apply our scientific understanding to real-world situations. Thank you. An example that came up with my own group not very long ago, I was teaching an AS physics course, which obviously included internal resistance of cells and so on. The question in the AS paper of that year had a question which was entirely about internal resistance, but the example it gave was one of those novelty clocks that's sometimes on sale. It was a basic digital clock, but the power source for the clock were two electrodes, and you put an onion or an apple or a piece of fruit in there, which acted as the electrolyte. And the idea is you put the two electrodes in there, so it was an apple clock or a potato clock or something that based on some, an electrolyte in the middle. And the number of students who effectively threw their hands up in horror and said, I haven't learned about fruit-driven clocks, and instantly didn't answer the question, even though the question itself, had they looked through it in any depth, was entirely about internal resistance, things they had studied and learned well. So it's building confidence that students think, okay, here's a question that looks new, but I have the confidence to know I've got the physics to be able to solve this. It's just then sorting out which bit of physics applies to this. And the question will usually make that fairly clear. It's that confidence that sometimes is the problem, to tackle the question that looks unfamiliar rather than physics knowledge and physics ability. We've mentioned exemplars a couple of times. Let's just have a look at those. A really useful resource for teachers and departments and for use with students are the exemplars. This slide shows the cover of one such, and they're all downloadable in PDF format under teaching and learning materials in the course book, on the website. So this shows the cover of one, which has marked examples of real students' attempts at the questions in a Unit 3 exam, such as the example given on the right-hand side of the slide. This example is not really for detailed discussion at the moment. We're going to get into that in a little while, but just to illustrate the type of information that's included. These sets of exemplars are also produced after each live exam series. So each examiner's report will also have exemplar materials. So under the examination materials on the website, if you see examiners' reports, they will have exemplars from those series. They're examples of one or more students' attempts at a question with the examiner's mark awarded and commentary on why that mark was justified. They're really good for getting inside the mind of the examiners, for distinguishing the features which make a good answer, and for learning how to interpret the mark scheme. Here's an extract from one of the exemplar materials available. I invite you to look at the part question that's shown on the blue background and the mark scheme, which I've shown down on the bottom left-hand side of the slide. On the next slide, I'm going to ask you to use this mark scheme to award marks for two examples of real students' attempts at this exact question. So you need to remember what the question is. A yo-yo is a toy that consists of two connected discs on a piece of string. I know toy shops don't describe them that way, but that's basically what they are. A child stands in a stationary train holding a yo-yo. The train accelerates and the string moves into the position shown at an angle theta to the vertical. So you can see the two diagrams. When the train is stationary, what is now effectively a simple pendulum is hanging vertically. And when the train is moving to the right, you can see that the pendulum swings and holds in a position slightly to the left at an angle theta to the vertical. The question is, draw the free body force diagram for the yo-yo when the train is accelerating. So the child isn't using the yo-yo in the traditional way up and down. They're simply holding it there like a simple pendulum. Okay, here's the mark scheme over on the left. It says one mark available for weight or W or mg labeled, and a second mark for tension. And the mark scheme also included a diagram to indicate what we're looking for. Okay, here are the two attempts then. I've reproduced the mark scheme again, so we don't have to keep flicking back to the previous slide. So the mark scheme is still there as before, but here on the right are two students, A and B, their attempts at this question. I'm not going to say any more. You have to decide what mark you would give student A and what mark you would give student B. Remember, the maximum mark for this question is 2. So the only possible marks are 0 or 1 or 2. So if you want to put into that, when you've marked it, if you want to put into the chat box, A and the mark you would give for A, and B and the mark you would give for B, and then we can compare notes in a couple of minutes. Just whilst you're doing that, I'll tackle the question that Kaj has just put in. Time management has been a very important problem for many students in completing their paper. Even I, as a teacher, feel this. So how can we deal with such problems so that students complete their paper in a given time? I will be talking a little bit about exam technique in a while, but cutting to the chase, I would say that often students run out of time by spending too much time on the multiple choice questions. My strong advice to students is to leave the multiple choice questions to the end. In very round terms, it's a bit more generous than this, but the amount of time allowed for an exam boils down to about 1 mark per minute. So a 1 mark question should be taking students a minute to complete. 2 mark question, 2 minutes, and so on. So the extended open response question is 6 marks. They got a good 6 minutes to complete it. In my experience, students who run out of time have often tackled the multiple choice questions and spent too long on them for what they deserve. If they're taking more than a minute to answer the question, they need to move on to the next one. It's very hard to discipline yourself to do that. A much better way around is to leave the multiple choice questions till the end, even though they're often at the beginning of the paper, and tackle the multiple choice questions last. Because if you run out of time on the multiple choice questions, you're only losing a mark per question. Run out of time in the questions later on in the paper, you're actually losing quite a lot of marks. So, some discipline, it's a particular problem for conscientious students because they'll often get stuck into a question and be determined to get to the answer, even if they're taking lots and lots of time on it. So I strongly recommend tackling the questions that are worth more marks earlier on. As I say, I'll talk through exam technique in a little while, but that will be a big thing to do. Don't spend too long getting hooked into a single question, particularly the multiple choice ones. Move on and come back to it if you've got time later on. Okay, we've got some suggestions here. A1 mark B2, A1 B2. Grace gives both 1. Clyde gives B 2 marks and A1. So 1, 2 seems to be a common answer. 1, 2, 1, 2, 1, 2. Oh yeah, that seems to be. Some people are giving 2 to both. Shazia has 1 mark each, and same with Samuel. Grace, that's harsh. 1 and 0. Okay. And A and 1, 2. So 1, 2 seems to me to be the most common one at the moment, but we've got a range of other, and that will always be the case. There's interpretation to be done here, and that's where the power of the exemplars comes in. Let's look at what the examiner said. Here they are. Okay, so the most common combination of marks that came in here is actually what the examiners came down on as well, which is a little bit reassuring. Here's the 2 examples here, and this is what the examiners said. Not me, the examiners who wrote the report on this paper. A, 1 mark. This candidate has drawn both of the forces expected to score the 2 marks, but has added in the components of tension in both the horizontal and vertical planes. This might have been acceptable if both of the components of T drawn had been dotted lines. In this case, the T sine theta is drawn as a solid line, in other words, the horizontal one. So this candidate scores just 1 mark. Okay, we might disagree with that, but that's the explanation that the examiners gave for their team decision. Remember, this is having gone through standardization and moderation processes. So this was the group decision on how to interpret that mark scheme in this specific case. Exemplar B got the full 2 marks. It says ideally, lines of force will be drawn using a ruler. However, this candidate has scored both marks, even though the lines are not completely straight. This is because it's completely clear which directions the weight and tension are acting. There are no additional forces drawn, so all is correct. Okay. Remember, the point is not really for us to challenge the way in which the mark scheme has been interpreted in this specific instance. We could all spend a lot of time doing that, and it might be fun, but that's not the purpose of this exercise. It's not really to challenge why it's been interpreted that way, but really to recognise that the exemplars are a very important tool, both for teachers and students, in finding out how the mark scheme is interpreted in practice by the examiners. And the more that you and the more that students look through these exemplars, the closer we get to knowing what's inside the inscrutable minds of the examiners and how we can get closer to satisfying them with our future answers. It really does show how the mark schemes are interpreted and what it is that distinguishes a good answer from a bad answer. When you do this with students, they're sometimes astonished to find that an answer which is only 2 or 3 lines long gets full marks, and an answer which fills the whole page and goes over onto another page only gets a small number of marks. Because if it meets the criteria of the mark scheme, it can be brief and concise and still get full marks. It's well worth doing this exercise with students. Yep, I agree, Grace. I've seen mark schemes that have done that as well. But what I'm saying is, I mean, I'm not an examiner, and the point of this is not for us to put our own point with the examiner. We might disagree with them, but what we're saying here is this is getting inside how the examiners are interpreting the mark scheme. Okay, so I'm not trying to defend it. I'm saying it's a really good way of finding out how the mark scheme is used by the examiners who are employed. Okay. In answer to your question, how do we judge when it's acceptable? I think what I'm saying again is that the exemplars simply give us an idea of how the markers, how the examiners are using these mark schemes and applying them and interpreting them. Okay, and I would say that the closer we get to being able to do that, the better we're serving our students, not because the examiners are 100% right, but because they're the ones giving the marks. So we owe it to our students to show them how the examiners are interpreting these mark schemes. Let's go on and have a quick look at the assessment of practical work and exam techniques. As mentioned earlier, all of the assessment of practical work is in the final written exams on units 3 and 6. It's about 20% of the total marks. There's no practical exam, no assessed practicals in this course. This increases the need over what might have happened in some older specifications for learning during practical lessons to be planned carefully so that students develop the skills that are necessary to tackle those exam questions. And the practical guide is an invaluable tool to aid this area of learning. You can download the practical guide in PDF form directly from the teaching and learning materials section of the website's main page. What's in it? Well, the practical guide for teachers includes practical assessment, assessment of practical skills, using core practicals to teach skills, mapping core practicals for maths skills development, teaching approaches to core practicals, answers to student guide questions, and answers to core practical questions. So there's a student guide as well, which is identical to the teacher guide, but doesn't have the answers within it. So that's the only difference between the two. And I know that some schools simply give students the teacher guide. That's a judgment to be made. But there is a student guide which simply has all the other information in, but misses out the answers to the example questions. So you can set them as homeworks and so on. Here's an extract from the practical guide regarding students keeping a record of their lab work. Student records. Possible formats for students to keep records of their practical work include a lab book. This has some advantages, mostly in being a working document where students can write notes on procedures, as well as take down data, sketch rough graphs, and so on. A folder of practical work, having the advantage of being able to store worksheets and other stimulus material alongside the practical notes, or integrating practical notes into the student's main folder. Whichever format you decide works best, it's important that the method of collecting and recording the practical work that students do meets the following requirements: to be a useful revision aid for students at the end of their course, and to allow students to record evidence in a variety of formats, such as diagrams, drawings, tables, graphs, and so on. This would also include space for any data analysis or evaluation. I would just say that sometimes teachers think, okay, sixth formers, to our A-level students, are effectively adults, so they can make their own decision on this. But remember, at the start of their course, they're effectively 1 day older than they were at the end of a GCSE course, and a little bit of guidance is helpful. It does say whichever format you decide works best. If you give it a free choice to students, that's fine, and some students will make the right choice. But if they make a choice that turns out not to work, if they don't realise till the end of the first term, it's really, really hard to go back and change the system when you've already put a term's work into a system that didn't work very well. So a little bit of advice and guidance from you about how to store this material in a way which is practical and most useful in terms of revision aid and recording different information is really helpful at the beginning. Here's an extract from the practical guide on core practical 5, which illustrates the type of practical guidance that's given within the book. You can see this one is about investigating the effects of length, tension, and mass per unit length on the frequency of a vibrating string or wire. And you can see it gives information about the experiment itself. It starts off with the 3 variables which can be tested, how students might write a plan and come to the lesson ready to carry it out. It's a bit more open-ended, so students need to keep a complete record. So there's information about the practical itself. Then some actual practical advice for the teacher. It says it's unlikely that centres will have enough vibration transducers for a class set. So if all students are to do this, a vertical alternative is possible. So it gives information and guidance about how to do an alternative method. So you might have all students doing it at the same time, but some using one method and some using another, or they might swap over and do both methods if you have time to do that. Or you might even run this with other practicals in a sort of circus so that all students move to this station at some stage. But you've got decisions to make. But it's looking at alternative methods of making the same physics learning in different practical settings. It does say at the bottom, safety should feature in all reports, but this one has it as a feature since there are wires under tension and hanging masses. So of course the risk there is that the wire can snap, the wire can spring back and catch somebody in the eye, so safety goggles will be important, and also the masses could fall and damage either the masses or the floor or the student's foot. So all of those are possible dangers to be thought about. It's often a comment when a question on safety is given in an exam question that students' answers are too generic. They'll just say something like always wear goggles or wear a white coat or something. What it's saying is think about what the specific risks in the experiment we're discussing and how could you minimize those risks. So students need to think of safety. How does it specifically relate to this experiment? And there's a mention there, as I say, in the core practical guide on this particular one. This and the next few slides show an example of a question testing practical skills. I'm going to prepare you. In a short while, I'm going to ask you to consider the implications of this type of questioning. How does it affect our teaching and learning while students are engaged in practical work? In other words, how can we teach students and enable them to learn from practical experiences so that they're well equipped to answer this type of question? So here's the question itself to start with. Student carried out an experiment to determine the mass per unit length mu of a string using a standing wave. The standing wave produced is shown in the diagram. The student recorded the following data as shown in the table. Calculate mu, in other words, the mass per unit length of the string, given the equation below, square root of mg over mu equals f lambda. So there's an example question from a past paper. It then goes on to give the mark scheme for part A. And a bit more of the question, identify 2 significant sources of uncertainty in the student's measurements. And for each of these sources of uncertainty, describe an experimental technique the student could have used to obtain an accurate measurement. And then there's the mark scheme for that part of the question too. And you can see you can get a maximum of 2 marks for many of the possible 5 alternatives shown there in the mark scheme. And for part B2, all of these possibilities. Remember, part B2 was for each of these sources, describe an experimental technique the student could have used. So these relate, depending on what sources of error they said, there are other possible exam answers of how they might have improved the accuracy of that. Okay, all within the core practical scheme. So in the light of those sections of the specification which describe what students will be assessed on in practical units and the example question we just looked at, What are the implications for our teaching and learning? Are there any things we need to think about when we're doing practical or experimental lessons to enable students to better tackle that sort of question that we've just been looking at? Remember, the question wasn't just asking them, what did you do in the practical or what did you find, but how could the practical have been improved? How could it be made more precise? All those sorts of things. I'll just give a couple of minutes while you think about and perhaps put comments on that into the chat. I won't give too long for this part. We're coming on next to have a look at a little bit at exam technique. It's a similar process to the earlier discussion on applying their learning to unfamiliar situations. Students find it really difficult to think beyond the boundaries of a core practical, in my experience, teaching the practical endorsement. Absolutely agree. So I think the answer you're leading us towards is you're thinking they need to think of the different possibilities. There need to be discussions about the issues we're talking about. In other words, how could we improve once they've done the experiment? What did you find? What was difficult? How could we improve it? It's the questions about devising a new experiment using practical techniques learned in the core practicals, but applying them to a different situation that students find difficult. And especially, how could you amend this practical technique to make it better in some ways, safer or more precise or more accurate, all those sorts of things. Okay, I teach intensive 4-day practical endorsements for distance learning students. Yeah, so you'll come across a lot of these issues really. Before they do the experiment, ask them for a risk analysis. Yeah, absolutely. And discuss those so students learn from one another, sharing ideas, because several people together will come up with lots of opportunities and they will all learn from that. Practical experiments related to the core practicals in the school and related to questions to be answered from the home. Yeah, I would agree. I think my main comment, and it's not really a throwaway line, but it's that I think we need to shift our focus, and I include myself within this, away from what are students doing in a practical towards what are students learning from a practical. A practical is not primarily a manual exercise, it's a mental exercise, and it's for us thinking, what are students learning when they're engaged in these experimental activities? And I think if we plan for that and include question and answer and discussions and plenaries and all these sorts of things to focus on what students are learning so that they can learn why we do the practicals this way, what are we trying to find out, what have we learned, how could it be improved, and so on, are really, really powerful. Practical experiments related to the core practicals in school also develop skills stepwise along with scaffolding. Yeah, so we start with early practicals, giving baby steps, as it were, and encouraging students, towards what we are, and improve students' skills of independent learning and more open-ended discussions the further we go through the course, so that students get used to asking themselves, what am I trying to find out in this experiment? Does this experiment accurately find that out? Students will sometimes say, my experiment didn't work, when they got a negative result. And of course, a negative result is just as important as a positive result, because it still taught them something that they didn't previously know. And it's getting students away from the idea of getting an experiment to work to getting an experiment to teach them something they didn't previously know. And that's a real step forward in scientific reasoning. And I think the key is getting students to think about, why are we using these techniques? Why am I using this apparatus? What am I trying to find out? How could I do this better? They can develop their own experiments to answer those questions. They've pretty much become scientists. Okay, as promised, I'm going to go on to have a brief look at exam technique. This shows the general rubric on the front of one of the physics IAL papers. You might want to think which points you'd particularly want to draw students' attention to. Have I got some arrows on here? I think I have. Yeah, there we go. These are ones that I'd want to highlight. There may be more space than you need. The key point is, have I answered the question which was asked, rather than have I filled the space provided? A look at the exemplars in the examiner's reports show that answers achieving full marks are not always longer than those achieving lower scores. That's the thing, as I said, that students often find most surprising when they look at these. Second arrow, showing the working in a calculation is essential. Already mentioned this. If the final answer is correct, then all of the marks are gained. But if the answer is incorrect, many of the marks can still be awarded for correct steps, including for steps correctly carried out with the wrong data from a previous step, what we referred to as ECF, errors carried forward. As a very rough rule of thumb, 1 minute per mark is a guide to the time to be spent on each question. I'll pick that up in exam technique later on. And finally, read each question carefully. Absolutely essential. Students often lose marks, and it's heartbreaking to see this when you look at students' answers. They often lose marks by not answering the question that was asked, but writing something else about the topic raised in the question. The answer they've given might be correct science, but if it hasn't answered the question, it won't get the marks. The command word is key to this. Racer said, what if the answer is correct, but the steps are wrong? They get the full marks if the answer is correct. That's the way the cookie crumbles, I'm afraid. If they've got the correct answer, then the steps aren't even marked. If the answer is incorrect, that's when the marker looks back at the steps to see whether they can glean any marks from that. So if they've achieved the correct answer using an incorrect method, they've fallen lucky. They still get the full marks for it. First part of a good exam technique is preparation. Practice is important so that students know what to expect and feel comfortable and confident when they see a paper. So they should practice past papers, but also have a chance to discuss incorrect answers and have another go, like we do with driving tests, so they can improve on what they did wrong. It can be done as self-assessment or peer assessment. We're going to look at one suggested strategy on the next slide. In preparation, I've said effective exam techniques need to be practiced by students using past papers or part papers, perhaps homemade papers using Exam Wizard tailored to you to suit the exercise or focused on a particular technique. Give students the paper to practice how to access it, give them the mark scheme so they can see what's expected by the examiners. But having a go-to strategy, a starting point, builds confidence and reduces the stress of what do I do first. It'd be hard to overstate the level of stress that many students feel when they enter an exam. Those first 5 or 10 minutes can be exhausting. And for students to have a guaranteed go-to plan, this is what I do in the first 5 minutes in an exam, can be really good for calming nerves and getting them to perform to the best of their knowledge. If you have yourself done recently even a driving test or a music exam grade or something like that, you'll be able to be familiar with how much the nerves can get in the way of a good performance. And some students, of course, suffer from this more than others. And it isn't the weaker students who suffer from this. The strongest and most confident students are the ones who really will be affected by exam nerves. So giving a strategy which says, here's where we start, this is what we do first, can be really helpful for those conscientious students. So here's a strategy that I've used with students, both at GCSE and A-level. Look through the whole paper first, underlining, or better highlighting, the command words in each question. Decide which question to do first. Start with the questions you feel most confident with, which is not necessarily question 1. There's absolutely no reason on God's earth why they have to start with question 1 and then do question 2 and then question 3 and so on. Often it's much more effective to start with 1 or 2 questions that they feel confident with, get those marks under their belt, calm down and be, on answering questions they know, and then they'll have more success with the questions they feel less confident with later on as they've sort of settled into it. Read the question carefully. Don't repeat the stem in your answer. Don't give up on a whole question. If you find one section of the question difficult, move on to the next part. The same strategy holds for whole questions that you find difficult. Move on. come back to missed questions and parts of questions when you've picked off all the low-hanging fruit. That's efficient as well as common sense. So we had a question early on about students' time management, not just about the time as well, though. If they're going to run out of time, it makes sense to run out of time on questions that they were less likely to get right anyway. So answering all the questions that they know the answers to picks up a lot of marks early on. If they then spend time later on in the exam tackling those little bits that they're not sure about using, then that's much more effective, because if they run out of time on those questions, they were questions they were less likely to get the marks on as well. And giving you time to just say, are there any strategies that you share with students that you found effective about exam strategy? I'll just pick up one or two of the questions that have come in on here. How are UK mark scheme different from international A-level mark scheme? I mean, I'd invite you to look at the two specifications, and you'll have to, of course, if you're delivering both of them. A big difference, huge difference really, is the way in which extended open response questions are marked. They're completely different in the UK and the international schemes. I mean, content is slightly different and other elements are different as well. Initially, international science papers were often assumed that international schools wouldn't have access to the same laboratory facilities. That's no longer the case often in many cases, but they developed in slightly different ways, and there are still differences. But as I say, the big difference at the moment seems to be the way in which the extended open response questions are marked. I do training both on international GCSEs and A-levels and UK ones, and that seems to be, to me, the most significant difference. As I say, the specifications do have slightly different content too, just because they've developed along slightly different lines, but that seems to be the big philosophical difference. Are highlighters allowed to be used in exams? Yes, the scanners that they use to send the answers off to the markers often don't show the highlighting, so the highlighting doesn't show up. But that doesn't really matter. The highlighter is for the purpose. The highlighter is not to show the answer to the examiner. It's for the purpose of the student themselves. If the candidate is using a highlighter to highlight the command word, for example, then there's no problem with that. Sometimes they can underline them with pen, or they can use a highlighter to highlight the command words. If they use a highlighter as part of their answer, they need to be aware that the marker might not be able to see it, but that's a different issue. So, I wouldn't use the highlighter to draw the answer or diagram, but to use it to highlight command words or highlight keywords in the question, not really a problem. Anyone got any strategies that they use? Oops, sorry, moved on. I didn't mean to move on there. Any strategies that you share with students for exams that you want to share with us? I will move on fairly quickly because we're pushing on with time. Okay, I will just mention then walking, talking mocks, which I mentioned on the GCSE course as well. This is a strategy which many people have reported they've had quite a lot of success with students, and it's basically walking, as a teacher, walking students through the strategy. I'll just pick up one or two suggestions that we've got coming in here. Use all of them, plus answers the topics you're strong in. Yeah, absolutely. And scrutiny by peers. Yeah, doing past papers and then discussing with a peer and saying what went wrong, what went wrong is really good and really efficient too. You can get through a lot in a lot of time if you as the teacher aren't having to mark every single attempt. Sorry, back to the walking, talking mocks. Students sit in the same exam room where they'll do their exam, preferably in the same seats. You can do it in your classroom, in the lab, but it's not always as effective in building confidence in exam conditions, in terms of calming those exam nerves. Students are given an exam paper, which is as close to being like the real thing as possible. Students are literally then walked through every question on the paper. So if you as the physics teacher are leading a walking, talking mock on physics papers, you would stand at the front with the paper on the whiteboard or whatever, projected on there so students can see the question that they've got in front of them. And you talk through your thought process. You underline the command word. You think, this is what the question is asking me. How am I going to start? I'll underline these key points. This is the equation I'm going to use, so I'll write that down. I might draw the data out of the question. So you do exactly what you as a physics student would do to tackle that question and talk them through as you do it. the smallest steps, underlining the keywords, planning the answer, things to remember. You might want to focus on a particular area, or you might want to look at the question as a whole. And then when you've gone through the paper, modeling how you would answer it and get to, as it were, perfect answers, then students write their responses. That's not a waste of time at all. They go through the paper. Hopefully they should get a really good mark because you've just literally told them how to do it. But it means having modeled it, they get an experience of going through a paper and tasting success, but also learning the methods that you're using to tackle it. People have reported really good results with this, so that they found it really helpful. Start with one we know to better to build confidence. Yeah, I agree. Yeah, I think that's like one we mentioned. In numerical answers, I sometimes give the answer and ask students to show the working to the answer as done in universities. Yeah, like reverse engineering it, as it were. How do I get to this answer? Yeah, that's good. So they know where they're going and they're specifically focusing on how you get there. Okay, thank you for those. There are Pearson videos available. You can download them online in the teaching and learning materials section of the website. You can find them on YouTube as well. And those videos are of science examiners and trainers delivering a few 10-minute walking, talking mocks. Those videos can themselves be used with students, but they're really intended to model how teachers might run walking, talking mocks themselves. So if you think it's a good idea, have a look at trying it. And it's something you can try and see whether it works for you and your students. You know, you don't have to take it on wholesale. It's a thing you can try with one and see how it works. Okay, we went through support yesterday, and because I think everyone on today's call was kind of here for yesterday, or you can look back at it, I'm not going to repeat all that. That seems a waste of your time. I will just mention the summary of it, reminding us that the support includes teaching and learning materials, past papers, mark schemes and examiners reports, teacher resource packs. Where do we find these videos? Grace has asked. If you go to the main page of which I'll show you next slide, the home page of the subject, it's within the link under teaching and learning materials. I'll show you when we get on to the next slide. There's also the teacher resource packs and published resources, student books, which give access to the digital versions of those student books with additional resources, and lab books as well. Here's a screenshot of the home page of the IAL Physics. You can see that there are hyperlinks all over the place here to Irene, or to the subject advisor, to registering your interest in it, the course materials on the blue background, and the videos are accessed under the teaching and learning materials there. So the third link down there. But there's also teacher support and training accessible, so you can see hyperlinks further down there. So basically the homepage, as you'd expect, is full of hyperlinks to other useful bits and bobs. The easiest way to find that page, in my experience, is to use a search engine. There are links and there are direct, what's the word I'm looking for? URLs, direct addresses, but it's much easier to use a search engine such as Google or DuckDuckGo or whatever, and type in IAL or International Advanced Level, Edexcel and Physics, and it will find this page. We've already discussed that. Not sure why that's coming up there. I'm going to click through the support slides, which we looked at yesterday, and leave us on the page with our subject advisor. There's Irene, who I already mentioned, who on the same email, and Tim Lawrence, who I think covers science and one other subject as well, psychology perhaps. teachingscience@pearson.com. And can also be contacted on the form via the Pearson website. Okay, we've come to the end of our content of this, well, both modules really. I'm going to go to a Pearson logo and we've basically completed the content of the course. Thank you very much for your participation, all the suggestions put in and contributions to the discussion. If you have no follow-up questions, then you're entitled to log off and leave now. And I say thank you very much. If you do have any questions, I will stay online and try and pick up those questions for a short while. Thank you very much. Enjoy the rest of your day and good luck with your students and their exams.